Our world is dependent on plastics. It is used in everything from food packaging, water storage, consumer products, tech, construction, and clothing. The estimated total annual plastic consumption of the world in 2020 was approximately 435 megatons. This consumption is only expected to increase, whereby in 2050 the projected consumption exceeds 800 megatons.
One of the world's biggest problems it is facing right now is its overconsumption of plastic due to its harmful impacts on our environment. Though using plastic itself is not directly harmful towards humans, the improper disposal, littering, and incineration of it pollutes our air, water, and soil. The most commonly used plastic, high-density polyethylene, can take up to 1,000 years to degrade. This means that all plastics ever created by humans have yet to fully break down. When plastic does partially degrade, it creates microplastics that leak into our water and food supply, causing health problems, worsening cardiovascular diseases, and infertility.
So, why is it commonly used?
Plastics, being a byproduct of crude oil processing, makes it accessible and affordable. Its molecular structure makes it extremely processable, where any shapes and sizes can be achieved with high strength-to-weight ratio. Its continued use despite its harmful effects could be attributed to the lack of readily available alternatives and innovation.
Plastic has been widely used because of its durability and accessibility, but concrete in many cases outperforms plastic in both strength and durability, especially in outdoor settings. Due to its low density, it is commonly used in marine infrastructure for bridges, pontoons, and docks. But with some innovation, concrete can be made buoyant as well.
Lightweight concrete that can replace plastics was achieved by incorporating ultra-lightweight aggregates into the mix. In this study, aggregate materials constituted 45% of the volume of the mix, whereas they were only 35% of the total weight. 3 different grades of aggregates made from hollow glass beads with bulk density ranging from 0.23 grams per centimeter cube to 0.53 grams per centimeter cube were used. Various types of supplementary cementitious materials, or SCMs for short, were incorporated into the mix. SCMs constituted more than 60% of the weight of the binder. For this, recycled materials such as ground glass pozzolan, or GGP for short, metakaolin, and silica fume were used.
To obtain the optimal water-to-binder ratio and the dosage of superplasticizer for concrete with sufficient strength and workability, fresh property tests such as flow table tests was conducted. With the developed mix design, a sufficient flow diameter of 168 mm was achieved. Most importantly, cubic specimens for 7th-day and 28th-day were cast. The 7th-day strength shows that this lightweight concrete can achieve a strength of upwards of 600 psi. Although this is not enough compressive strength for structural grade concrete, however, it can compete with plastics that are used in infrastructure and marine purposes.
Finally, the density of fresh and hardened concrete was measured to see how buoyant the structures are going to be. A hardened density of 0.89 grams per centimeter cubed was achieved, which is less than that of water. By leveraging placement of air pockets in the modular pieces of the floating infrastructure, not only can a floating structure be achieved, but it can also carry loads exerted by humans.
Although a mixture with adequate mechanical strength, reduced density, and satisfactory fresh properties was successfully developed, its practical implementation in modular floating bridge systems requires further investigation. Future research should focus on the design and validation of modular units, particularly addressing connection mechanisms and internal structural configurations. The connections must be sufficiently simple to enable efficient assembly while maintaining the structural integrity necessary for effective load transfer between units. In addition, the incorporation and optimization of internal air gaps are critical to ensuring adequate buoyancy such that the system can safely support the anticipated service loads.
Overconsumption of plastic is a growing problem where it is vastly polluting the earth. In particular, it is contaminating our water supply and oceans. Concrete may help to alleviate some of the accumulation of plastic waste, where it can supplement large uses of plastic in construction and recreational design. Lightweight concrete offers an innovative and unique solution to construction in marine settings where it may replace unsustainable uses of plastic in infrastructure.
Our goal is to have plastic-free waterways and infrastructure that is both sustainable and durable.